Hello and welcome to Carl and Cymru e-sgol sessions. My name is Mr. Ridd and I will be taking you through AS Unit 2 Photons 2.7. I just want to make clear as well that this is just one of many sessions, a lot of which have been pre-recorded. And if you'd like to access some of that previous material, then all you need to do is check out the e-sgol website. If you Google e-sgol, click on the link and you will get this home page. Follow the Carl and Cymru link as you can see on screen there, and you can access like a whole library of previously recorded material which would help you, I hope, to pass those dreaded exams or just learn a little bit of physics, whatever you prefer. Right, anyway, on to photons then. And to begin with then, I think it's worth just asking this question, right? What is a photon? What is light? Is it a particle or is it a wave? And the answer to that is kind of like yes, which is a silly answer, I know. But depending on the circumstances, light can behave like a wave or it can behave like a particle. Now, that as a concept in and of itself might sound utterly ridiculous, and that's correct. It is not something that is easy for us to conceptualize, how something can be spread out like a wave, yet in certain circumstances also behave like a point, like an object, like a particle. It is something that, you know, even the smartest physicists in the world have to wrestle and grapple with, and not something that anyone can truly conceptualize. So don't feel like you're on your own. It's confusing to all. So light is a wave and it is a particle depending on the circumstances. Now, to begin with then, if we look at the content that we've got to go through, and this is taken straight off your specification for the course, you can see that point A, the fact that light can be shown to consist of discrete packets or photons of energy. So one way to conceptualize what's going on here is to think of light or a photon as a discrete bundle, little packet of energy. And, you know, it's not perfect, but you can kind of think of it a bit like that image then, like a little concentrated packet of a wave, right? And that will do just fine. I don't think we need to go into any more detail on that, okay? But it's not I say a concept that's easily understood. The energy of a photon then is given by this formula here. Let me just close this a second, more screen. E is equal to hf, and this was put forward by a very famous physicist known as Max Planck. And in fact, this equation, without going into too much detail, and the implications of the fact that energy was quantized, i.e. came in certain values, was such a groundbreaking discovery and idea that it really was the start of what we now call quantum mechanics, a whole branch of physics. So when we're calculating the energy of a photon, I might be skipping a little bit further ahead here, we use this formula, the energy of an individual packet of light. E is equal to hf. So in this, E stands for energy, H stands for Planck's constant. And, you know, if you do something really awesome in physics, or science in general, then you get a constant named after yourself. Isn't that cool? And Planck's constant here has this value, 6.63 times 10 to the minus 34 joule seconds. It's a very, very small number. And the size of the number is partly the reason why it took so long to discover quantum mechanics, because the gradations of energy, the difference between the energy of one photon and another, is so minuscule it could have been thought previously to be continuous. Anyway, sorry, I digress. So we're going to leave that there, all right? And we're going to say that, do you know what? This first one here, we're going to say done. The fact that light can be shown to consist of discrete packets or photons of energy is just a fact you need to know. So moving on then, how the photoelectric effect can be demonstrated. Let's get on to that one. Now, the photoelectric effect, to give it a little bit of a backstory, essentially broke physics for a while. So there was a classic theory of how light behaved as a wave. Classical physics, as it's called. And classical physics, in a nutshell, and I don't want to go on for too long here, because it will get us off what this is, which is a revision video after all. Classical mechanics could not explain certain phenomena that were observed experimentally. What do I mean by that? Well, one such and very, very important example is known as the photoelectric effect. The photoelectric effect is essentially occurs when a radiation of a certain energy, in this case UV light, as we can see here, is shone onto a metallic plate or a charged metallic plate. When that happens, electrons which are on that plate may well be what we refer to as liberated, or they may escape from the surface of the plate. And the mechanism by which this happens is that the electrons absorb energy from that light source, and in gaining that energy, they overcome the amount of energy they need to escape the surface of the metal. Classical mechanics could not explain the photoelectric effect, because it was believed previously that if you had a really, really bright red light of a greater intensity, so a lot of bright light, then you could essentially liberate electrons from any surface. However, when we observed this in action, what we found was there was no amount of red light, for example, that could cause electrons to be liberated or escape from a zinc plate, as in this particular diagram. And in fact, it had nothing to do with the amount of light that you had, the intensity, how bright it was, but everything to do with the wavelength. And classical mechanics really was broken at this point, because it couldn't explain how even a very dim UV light, so very weak, not very bright UV light, would nevertheless cause electrons to zip off the surface of that metallic plate. This, incidentally, here, you might have seen it in school. This is known as a gold leaf electroscope. And it's kind of a nifty way of, or simple way of measuring charge, because if I charge this zinc plate at the top, then the electrons, in this case, the excess electrons, will form all over, here look, all over this metallic rod and the surface. And then down at the bottom here, what we have is a little piece of, you can see it in the diagram, gold leaf. And gold leaf is just a really thin piece of gold, okay? Like gold foil. And essentially, when the whole rod and the gold leaf become charged negatively, then it will cause the gold leaf to displace. It will cause it to, if you like, rise. And the reason why it rises is because the rod is negatively charged and the gold leaf is negatively charged. And therefore, they will repel each other, causing this, this movement, okay? Here's the thing. As we shone the light source then, the UV light source, onto the surface of that zinc plate, over time, because those electrons are escaping, what it meant was this gold leaf down the bottom here would gradually come down as the electrons left this system, shall we say. As the charge leaked away, that force of repulsion got weaker and weaker, and eventually we'd notice, of course, that the gold leaf electroscope had completely discharged. Now, there are more sophisticated ways of doing it today, but essentially that still serves a purpose, and as a visual demonstration, it works really, really well. So yeah, back to the physics here. So how can we explain the photoelectric effect now, and why do photons come into a photons, I should say, not photons. Why do photons come into the equation here? Why are they an adequate explanation for why this happens? Well, if we imagine now that light is not a continuous wave which will eventually cause all of the electrons to gain enough energy to leave, if we imagine that light actually travels as discrete packets, those photons that we mentioned earlier on, then we can use that to explain how electrons are emitted from the surface of the plate. And one way sometimes I like to try and describe this is by imagining that we've got like a hill, okay? And imagine you've got an electron at the bottom of that hill. And there's a certain amount of energy, right, that it needs to gain in order to get to the top of that hill. And what we imagine is that a photon is a bit like a kick on that football. When the electron absorbs that photon, if the photon carries enough energy to kick the ball up to the top of the slope, then the electron, or in this case the football, will leave that dip, it will get to the top of the slope, and it will have left, if you like, the surface of the metallic plate, or it would have left the bottom of the hill. However, should it be the case that the kick that we give that football, should it be the case that the energy in that photon is not sufficient to overcome this amount of energy required, right, in order to get up the hill, then the electron and the football, if you like to just carry on the analogy, will not make it to the top. It will get maybe so far, and then it will roll back down. And this allowed us to explain the phenomena that we observed, which I mentioned just now. Because no amount of red light, no amount of small kicks were ever able to get the electron to leave. No amount of small kicks were ever able to kick that football up the slope. Every time it came back down and got another kick, it still wasn't enough to get to the top. However, even if we have a dim UV light, and what that essentially means is that we haven't got many photons per second, there aren't many photons being emitted each second, then even if one of them is absorbed by an electron, it will still be enough energy to send the football to the top and escape. It will be enough energy for the electron to escape the surface of the metal. And it's only in considering the absorption of the energy as a discrete packet or burst, like a kick, that we're able to conceptualize how red light can't cause this phenomenon to happen, as I previously mentioned, but UV light can. Remember, no amount of red light, no intensity of red light is capable of causing this to happen. But even a low intensity UV light is able to do so. And it comes back to that formula which we mentioned earlier on, E is equal to HF, okay, in which the energy of every individual photon is given by its frequency, or if you like, the energy of every individual photon, to rewrite it, is given by, if you like, its wavelength, or the inverse of its wavelength. So this little cartoon kind of nicely illustrates what's going on with the photoelectric effect. So if we have low frequency photons, then they are able to cause the photoelectric effect to happen, potentially, as long as they're able to overcome that amount of energy required to leave the surface of the metal. In other words, back to our analogy, as long as they're able to overcome the amount of energy required to get up the hill. However, if a photon only provides just enough energy for that electron to escape, and that's equivalent of us just about kicking the ball hard enough to get to the top of the slope, then the amount of energy that the photoelectron leaves with, and that's what we call them photoelectron, the amount of energy that it leaves will be very low. So we'd say it has a low amount of kinetic energy leaving the surface. However, if we have a higher frequency, look, so that was lower frequency. If we have a higher frequency, then not only will it have enough energy to get to the top of the slope, but it'll have plenty of energy left over. In fact, the photoelectrons, these electrons that be liberated, will now have energy to roll up the slope and beyond, and they'll have kinetic energy to spare. Again, it's like kicking the ball really hard up the slope and having it shoot off. All right, so that's what happens with a higher frequency. You end up with faster photoelectrons. Now, back to intensity now. And now we're going to conceptualize what intensity means in terms of photons. Intensity, in terms of photons, just means the number of photons per second. So as I shine my light onto the surface, if it's a low intensity or lower intensity, it means that there are less photons hitting that metallic surface each second. So then we're not going to get as many photoelectrons leaving. However, if we have a higher intensity, that means that we have more photons, and therefore we will create more photoelectrons, as you can see illustrated in that cartoon. All right. But very importantly, a higher intensity, as we have here, higher intensity does not mean higher energy for every individual photon. So yes, there are more photoelectrons, but it will not increase, okay, it will not increase the kinetic energy of each individual photon. Okay. So now that we've got that out the way, we're going to talk about how we could measure the photoelectric effect. So this experimental setup shouldn't really freak you out too much. It's relatively straightforward. Let's go through it together. Here we have what we call a photocell. In the photocell, we have a metallic plate, as you can see at the bottom here, and incident light. Now, for the photoelectric effect to happen, the incident light has to have photons that contain enough energy to cause the electrons to escape. And like back in the previous example we looked at, it would have to be something like an ultraviolet light source shone on a zinc plate. Now, different metals have different, if you like, requirements. They all have a different amount of energy that they need to receive in order to give up a photoelectron. More on that in just a second. But let's just stick with the example that we had just now. So let's just imagine this is UV light, and this here at the bottom is our zinc plate. As the light hits that zinc plate, then we're going to release these photoelectrons as indicated here. Now, they are going to travel, okay, from, let's see, the anode to the cathode. In this case, then, this will become positive, and this will become negative. Go from anode, that's not very good, is it? Come on, try that. To cathode. And essentially what we'll have here, because we've got the movement here of charge, then we've got a small current. And that small current can be measured using our ammeter. This is quite a special ammeter. You can see it's got this little prefix here. All right, that's a mu, standing for microammeters. This is measuring very, very small currents. So this microammeter is going to measure a very, very small current. Now, here's the thing. What we want to do, if we're measuring the photoelectric effect, is we'd love to be able to work out things like how much energy is required for these electrons to be liberated. Now, we call this the work function, okay? And it's got a symbol psi. It's known as the work function. And I'm going to mention this a lot. It is the energy required for, or if you like, for an electron to escape the surface of a metal, the work function. And we can actually use this experimental setup to determine that. So we're measuring this small current on our microammeter at the bottom, and then what we need to do is provide a voltage in the opposite direction using our variable power supply, just here. And we're going to call this voltage that we supply to oppose our current that's been set up by our photocell. We're going to call this our stop-in voltage. Stop-in voltage, or if you like, stop-in PD, stop-in potential difference. Now, a way to think about this is, have you ever put the batteries the wrong way around in a remote control, for example? You put 2 fresh batteries in, you're like, yeah, happy days, Netflix, let's go. But nothing's working. What's going on? Oh, I put the batteries in wrong. What's happening there? Well, you've got one battery, maybe a 1.5 volt battery pushing one way, and because you've inserted them wrong, you've got the other battery, I should call them cells really, but you know what I'm saying, pushing in the opposite direction. So essentially what happens is you've got one voltage pushing one way, you've got another voltage pushing the other way, and they cancel each other out. And that's what you want to try and do here, except you've got this voltage created by the photocell, and what we are going to do, we're going to provide a counter voltage in order to stop that current from flowing. How will we know the current stopped flowing? How will we know that we provided exactly the right stopping voltage? Well, that's when the microammeter, okay, when this equals 0. So when the current completely stops, we know we've done a good job. Okay. So here's the thing. We've got these electrons, right? The electrons are going to have kinetic energy. We often call this EK max. They're going to have a certain amount of kinetic energy, and remember, that's the kinetic energy that they've got left over after they've gone up the hill. All right. So the electrons have absorbed a photon. That photon's given them a kick. They've just about overcome the amount of energy required to escape the surface of the metal, which we call, that was a shame. Oh dear, draw. Which we call the work function. And then whatever's left over is their kinetic energy. Now what we want to do is stop that. We want to take away that kinetic energy. We want to do work against them equal to the amount of kinetic energy they got, because at the moment that kinetic energy is causing a current to flow, and if we provide a stop-in potential or stop-in PD, then what we'll have done is we'll have done work against those electrons to slow them down and stop them. It's a really difficult concept. I'll put it in a really simple way though. Imagine you're in a car. I was going to say imagine you're a car then, but that doesn't make any sense. Imagine you're in a car and you're traveling towards a set of traffic lights, and then they go red. Now, you have a certain amount of kinetic energy as you're traveling towards those lights. To stop you, you have to, or the brakes have to do work equal to the amount of kinetic energy that you have, and they have to dissipate that kinetic energy to bring you to a stop before you run the red light. It's the same kind of thing here. These electrons have got a certain amount of kinetic energy, and what we're going to do is we're going to do work against them to slow them down and stop them effectively. Now, work done is equal to Q times V. And you'll know this equation already, I hope, from the work that you've done on electricity. You should know that V, the potential difference of the voltage, is equal to W over Q. You'll have come across that already. I've just rearranged it. So the work done on a charged particle in an electric field is given by this equation here, okay? So, here's the thing. if we want to stop our electrons, we have to do work must equal the kinetic energy that they got, which is Ek max, and that must be equal to the charge of an electron, Q, which is known as E, which is 1.6 times 10 to the minus 19 coulombs, times this stopping voltage that we need to apply. So we adjust the voltage so that no current flows, and when that happens, we know we've done exactly the right amount of work to, if you like, negate or against the kinetic energy that the electrons have. And here's the thing, if we know that stopping voltage, then we know Ek max. Right, so that's essentially how this works, and of course this here is our voltmeter to measure that voltage, that stopping voltage that I was talking about just now. Right, now here's the thing, I'm going to show you a kind of a complicated formula now that, if you like, consolidates everything that I've just been saying. So to begin with, we have our photon energy, HF. That is going to be absorbed by an electron. We've also got this concept of the kinetic energy of the electron, Ek max, which is the energy that we've got left over. And you've also got the concept of the work function, which has got the symbol psi. And the work function is the amount of energy needs to be overcome in order to leave the surface. You can think of this, psi, you can think of as a bit like the height of the hill. Kinetic energy is how much energy the ball has at the end. HF is how much the energy the ball was given to begin with. So essentially, you can think of it like this. Ek max, the amount of energy that the electrons have at the end, is going to be equal to the amount of energy was given to begin with, HF, minus what it had to overcome to escape, which is psi. And this equation, you'll see in your textbooks, it's a complicated one. It's got a lot of meaning in it. I just hope you understand it a little bit better now. We're going to compare this to y is equal to mx plus c, as we do so often. So y is equal to mx plus c. In that situation then, Ek max would be on the y-axis. Now h we've already mentioned before, that's Planck's constant. F is the frequency. So if we adjusted the frequency as another variable, that would be like our x. The gradient m would be h, Planck's constant. And then finally the intercept. Remember now, c is the intercept on the y-axis in the straight line equation, should give us our work function. And you'll notice it's negative as well, so we should have a negative intercept. Right, sure enough, if we do that, we plot Ek max on here. But we have to remember that we know what Ek max is, because if we do in this experiment, we have already just proven that Ek max, look, can be determined by applying a stopping voltage, measuring that stopping voltage, and remembering the formula for the work done on a charged particle. So actually, if we plot, if you like, E vs or Ek max, it's the same thing on this axis. Okay, just going to get rid of this guy a second. Right, now, what do we find? Well, let Mr. Rigg get his ruler out here. What we find is we end up with something that looks a bit like this. Okay. Now there's a few things that we need to just appreciate about this line. First of all, the gradient of this line. Okay, so the gradient is equal to Planck's constant, h, which as we mentioned earlier on is 6.63 times 10 minus 34. We also need to appreciate this down here, the intercept on the y-axis. Now this here is psi. Oh, it's a terrible psi. Or the work function. And here is an interesting part. Now that I don't know why it's done that. Let me get a better pen. There we go. Here we have this interesting intersection here. So what is the significance of this point on the graph? I hear you ask, but I'm glad you asked because I'm going to tell you. At this point here, look, it would be fair to say that the photoelectrons, this is 0, the photoelectrons have 0 energy. Anything less than this frequency, remember now we've got frequency on this axis, anything less than this frequency here, and we're in this region at the bottom, right, we're down here, anything less than that, and the electron has not received enough energy to escape. Back to the football thing, it's like we haven't used a kick, we haven't kicked it with enough kinetic energy to get it up the hill. So any frequency below this, what we call, and we're going to name it now, okay, the threshold frequency. The threshold frequency. Any energy less than that is not going to cause a photoelectron to be emitted. You will not observe the photoelectric effect, which again is the reason why red light of no intensity is capable of causing the liberation of electrons. So we call this the threshold frequency, sometimes F0, and it is, if you like, the minimum amount of energy, or the minimum frequency, and therefore energy, really, because don't forget, E is equal to HF. It is the minimum frequency required for the photoelectric effect to be observed. Because at this point, the electrons will have 0 kinetic energy that will just be liberated, but not have any kinetic energy left over to spare. What do other metals look like? So we've mentioned zinc. You might have another metal which has maybe a lower work function. It requires less energy to be liberated. Now such a metal, I'm not going to pretend I can name one I can't think off the top of my head. Sorry. But let's imagine another metal, let's say magnesium, right? But it might not be. If it had a lower work function, then it would have exactly the same gradient as we've indicated here. Because remember now, the gradient is Planck's constant, so that can't change. It has, if you like, less energy needed to be overcome in order for an electron to escape. So it's got a lower work function, and it will also have a lower threshold frequency. Right, so we've covered quite a lot there. Let's see which parts of this specification now we can check off. So how the photoelectric effect we demonstrate, that was the gold leaf electroscope. How a vacuum photocell can be used to measure maximum kinetic energy, EK max, of emitted electrons in eV and hence in joules. Now we haven't talked about electron volts and joules, but we will do shortly. But suffice to say that electron volts and joules are just 2 different measurements of energy. Yeah, so we'll get to that in just a moment. The graph of EK max against frequency of illuminating radiation, which we just looked at, that's the last thing we did. How a photon picture of light leads to Einstein's equation EK max is equal to HF minus psi, or the work function. We've looked at that. And how this equation correlates with the graph of EK max against frequency. Double thumbs. Okay. Next, we're going to look at the fact that the visible spectrum runs from approximately 700 nanometers to 400 nanometers. And we're going to look at the orders of magnitude of wavelengths of the other named regions of the electromagnetic spectrum. Right. So first of all, we'll start off with the visible spectrum. I'm sure you've all seen this image before. This, of course, famously on the cover of a Pink Floyd album. But more importantly, am I allowed to say that more importantly? I'm sure a lot of Pink Floyd fans would be going mad right now. But it is more, I'm sorry, it is more important. This was an experiment which proved that white light was in fact comprised of lots of different colours, and it showed the different parts of the visible spectrum. And the physicist to do this, of course, was Sir Isaac Newton. And this, in many ways, is the most important experiment that's ever been done. In fact, you could say it is the experiment. All right, it's that significant. And I'll let you figure out why. You go do some Googling, work it out. But it was a really, really big deal. Now, Herschel, Frederick William Herschel, did an experiment using a prism, and it was quite a remarkable experiment, because in that experiment he discovered that not only is there red light, but just beyond red light, like up here, is what we call, well, it was like an invisible kind of light, and he called that infrared, beyond red, if you like. And that was sort of like the key to opening the door of accepting and trying to find out more about these other types of light that might be invisible to the human eye. So here we have the visible spectrum. As it said in the specification, the shortest part then would be 400 nanometers. And remember, that's 400 times 10 to the minus 9 meters, up to 700 nanometers at the other end. Then you've got the different parts of the spectrum, go from gamma rays, which have got a wavelength of in the order of 10 to the minus 12, about the width of an atomic nucleus, all the way up to radio waves, which can be anything up to like a kilometer long. All right, so, and everything in between. You'll have done this to some extent at Key Stage 4, so you should know the order of the electromagnetic spectrum. But in terms of knowing what the typical wavelengths are, that's just something you're going to have to learn. So I'm not going to spend time just talking about that now. It's not hard. It's just something that you have to commit to memory. All right. So that is the electromagnetic spectrum, and in particular, that is the visible spectrum there. Let's see if we cover everything there. So I'm going to say that one is done. You can learn the wavelengths yourself. Typical photon energies of these radiations. So a typical photon energy then for these radiations, to work that out, what we would need to do is use that equation, E equals hf again. And then quite simply just either work out what the frequencies are or use a slightly different iteration of this. So C, speed of light, this is the wave equation, is equal to f lambda. So f is equal to c over lambda, and therefore I can rewrite this first equation as E is equal to h c over lambda. All right, and a typical energy then, so we'd be using 6.63 times 10 to the minus 34 times the speed of light c, which is 3 times 10 to the 8, all over lambda. Let's say if we were going for violet light here, or blue light, or that end if you like, then it would be something like 650 for the wavelength times 10. Oh, that's wrong. I told a lie. Remember now, the violet or blue end is the shortest, so that's the 400 nanometer part. I was just testing it really. So that's 400 times 10 to the minus 9. And you chuck it all on a calculator and you'd get your own typical photon energy. Alright. I haven't got a calculator with me right now, but I'm sure you can all do that, no problem. So that's how we'd work out a typical photon energy. As long as you know the wavelength or the frequency, you use E equals hf, and you're laughing. Job's done. I've already ticked that one. How to produce line emission and line absorption spectrum from, let me try that sentence again. How to produce line emission and line absorption spectra from atoms. Right, let's have a look at that. Okay. I'm going to jump ahead a little bit here and start talking about energy levels. So I think it helps us understand this point a little bit better. So here is a representation of an atom. And this would be something simple like a hydrogen atom, because it's just got one proton in the center. Hydrogen atoms, like all atoms, have electrons which orbit the nucleus, although that becomes less and less true the more physics you study. But for now, we'll say that that kind of works, even though they're kind of in a diffuse cloud, but that's okay. These electrons that you've been told previously are in shells that orbit atoms can occupy different energy levels. And when an atom becomes excited, not like that, but when it gains energy, electrons are promoted or occupy higher energy states. And a way of representing that in a diagram is here. And we say that you've got your lower state, okay, often referred to as the ground state, n equals 1. But then an electron can, if it absorbs energy, could be a photon, could be, undergoes a collision, whatever. If it gains energy, it can put an electron to a higher energy state. So an electron might jump from here to here. Now, a really important aspect to all of this is that electrons cannot exist anywhere between states. And this is why we do not get a continuous spectrum of energy when we look at the emission spectrum of hydrogen, for example, or any element for that matter. The energy emitted is always one energy or another. And as such, every single atom, every single element has its own characteristic sort of signature. It has its own permitted energy levels and energy states. And electrons can either jump from maybe n equals 1 to n equals 2, or it can jump from n equals 1 to n equals 3. And I think you know what's coming. You can go from n equals 1 to n equals 4. Could even go from, if it's already there, it could even go from n equals 2 to n equals 4 and all of the other permutations in between. But it cannot exist anywhere between those energy states. It's a bit like the floors of a hotel. Electrons can occupy different floors, but they're not allowed to sleep on the stairs in between the floors. All right, or the lift doesn't stop in between the floors, okay? It only will be on one floor or the other. Now, okay, Mr. Reed, what's this going to do with photons and spectra? Well, here's the thing. Just in the same way that if an electron gains energy, goes to a higher energy state, at some point it's got to come back down. And when it comes back down, like in the case of this guy, it can go from the top here down one energy level, or it could go all the way down to the bottom, okay, back down to the ground state. When it does that, it loses energy in the form of, you guessed it, a photon. And that photon energy corresponds to that transition, that change in energy levels. And what's important to note here is that I've drawn one going from, let's see, n equals 4, this is the top one's n equals 4, down to n equals 1. That's quite a large, if you like, energy transition here. It's quite a significant loss of energy. In the analogy of the hotel or the different floors of a building, it's like going from the top floor down to the bottom floor. So there's a big loss in it of gravitational energy in that sense. So it could have, though, gone from this n equals 4 down to n equals 2. And then it would lost a photon of a lower energy, which I indicated with a longer wavelength. Wasn't that clever? So there'd be less energy emitted in that photon, and it would have a longer wavelength to, accommodate for that fact. We can represent all this in the following diagram. So rather than drawing it as a circular atom now, what I'm doing is I'm drawing these different energy levels, okay, as sort of like discrete lines. And another point worth noting on here is I've also put on this n equals infinity here, which is essentially when an electron gains enough energy to escape the atom, right? And we call this ionization now, right? Because the electron will no longer be part of the atom will become an ion. And then the other thing about these energy levels, you notice on the left here, is they correspond to different sizes, they have different magnitudes as indicated here on the left. Now, you might well be asking yourself, why is this minus 13.6 eV? Why is it just not 13.6, or why is this not 0 and then it has to like get up to 13.6 eV to leave? Well, it's a good question, but the way I want you to try and conceptualize it again is like by considering this to be the amount of energy required for an electron to become ionized or escape an atom, a bit like with the photoelectric effect. And as such, it's the amount of energy that needs to be overcome. So if I was to give 13.6, exactly 13.6 electron volts to this electron in the ground state as it resides, then it would essentially become an ion, but now it would have zero energy. All right, it would have, if you like, paid exactly the amount of energy it needed to escape and no more. So therefore, we think of it a bit like a potential well, sometimes we call it. Okay, it's the amount of energy that needs to be overcome to get from one state to another. So there are lots of permutations. So you can have electrons going from, oh, sorry, not that one. Forget that one, because we've already got an ion by that point. Here, we can have it go here, or we could have it go here. Similarly, though, we could have this transition, and we could have this transition, or just simply this transition. What I'm getting at here is there are certain numbers of permitted transitions from higher energy states to lower energy states, and therefore there will only be a set of finite number of possibilities for photon energies that can be produced. Right, so we can look at this using a couple of methods, right? One would be a spectrometer, or we can look at it through a diffraction grating. And essentially what happens is, just like with the prism, we take the light that comes from an atom and we will split it up into different wavelengths. Just like the prism refracts blue light more than red light, the diffraction grating, or the spectrometer, is going to diffract blue more than red, and it's going to split the emission spectrum of a hydrogen atom, or any atom for that matter, any element, into very discrete wavelengths, which we can see indicated here. So this is the hydrogen spectrum. We can see these very distinct wavelengths of light that have been produced when those hydrogen atoms are being excited. We call these emission spectra, and they correspond exactly to those transitions from those permitted energy levels I mentioned earlier on. So if we were to heat a gas, okay, hydrogen gas, then what we'd see if we observed it, okay, through a prism, we would see all of these different definitive lines, which we would call an emission spectra. However, we do also sometimes observe absorption spectra. So if we're looking at a distant star, for example, we'd actually see maybe, and let's say we had a cloud of hydrogen in between us and that star, and let's imagine we observed that, again, through maybe a prism which split up the light for us, then what we'd observe is the light from the star being a continuous spectrum, i.e. all of the colours of the rainbow, which I said I wouldn't say again, we shouldn't say anymore, but that's what you'd observe. So you'd observe a continuous spectrum. What you'd see is, because it passed through this hydrogen cloud, you'd see certain wavelengths of light missing, because The hydrogen atoms in that cloud would be able to absorb certain photons, which correspond directly to those energy level transitions. And when it does that, the electrons will go into higher excited states. But at some point, they would jump back down again and re-emit those photons. But here's the thing. The hydrogen cloud would re-emit those photons in some random direction. Could be slightly in our direction, but more than likely in some random direction. And those photons that have been emitted by the hydrogen gas would therefore be missing from the continuous spectrum that we can see up here. Okay, they would be missing from this continuous spectrum that you can see here. So, just to recap then, the light from the star will go through something like a cooler gas cloud. The continuous spectrum containing all the colors, some of those photons would be taken up or absorbed by the hydrogen atoms. Only the ones, though, that correspond to that transition in energy level. And then they'd be re-emitted in some random direction. And that random direction would almost certainly not be in our direction, and therefore those lines would be missing from the absorption spectrum. However, it is worth noting, of course, that the absorption spectrum perfectly matches the emission spectrum in the sense that the lines or the dark bands are in the same places. So, let's go back here then. How to produce line emission and absorption spectrum atoms. Job done. The appearance of such spectra as seen in a diffraction grating. All that is this image here. So use a diffraction grating to split the colours up and to be able to view the spectrum. Simple atomic energy level diagrams together with photon hypothesis, line emission and line absorption spectra. How to determine ionization energies from an energy level diagram. So this one here, point K, how to determine ionization. Well, if you look at the ground state here, 13.6 eV, that would quite simply be the amount of energy required in order to ionize that atom and to give the electron enough energy for it to be ionized, okay? And just while we're at it, converting between electron volts and joules. So 1 eV is equal to 1.6 times 10 to the minus 19 joules. All right, that's 1 electron volt. It's just a very, very small unit of energy. You do have to learn to derive that, but that's for another time. And then a demonstration of electron diffraction, and the particles have a wave-like aspect. Okay, we'll go through this, I think, and then we're going to have to call it a day because this is getting a little bit on the long side now. So, one of the wackiest things about this particular topic, it sort of links back to what I talked about at the start, and the question of, you know, is light a wave or a particle? And the answer is kind of like, well, it is both. Famously, de Broglie asked the question, well, if light can behave as a particle, then can a particle behave like a wave? You know, if a wave can behave like a particle, does this door swing both ways then? Okay, and what we did was we started firing electrons, which are tiny, 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 tiny particles, leptons, some of the smallest we know. We started firing them at like really small gaps. If you remember anything about diffraction from the work on waves that is another part of Unit 2, then you remember that diffraction occurs when the wavelength and the gap through which the wave passes are of a similar or comparable size, okay? And when that happens, you get maximum diffraction, you get the spread out of the wave. So if you were to fire electrons, which don't really have a perceivable wavelength, or so we thought, through a really small gap, then what might happen? Well, the gap that they decided to use is sort of like the lattice structure of, I think they use graphite, but you can actually do this with all kinds of materials. When you fire it through these really small gaps, which are really the interatomic spacings between atoms, at very high speeds, then you end up with this incredible diffraction pattern, as shown by these rings here. And it's just one of the most remarkable consequences of our understanding of physics in the last century. What it shows is that the particles, or what we thought were particles and only particles, i.e., things of mass concentrated in one place, can actually behave like waves, because what you're seeing with these rings here is regions of constructive and destructive interference. Now, when you've done waves, you'll know that where you see dark fringes, that's known as destructive interference, and where you see bright fringes, that's known as constructive interference. In case of waves, it's where constructive interference is where two peaks line up, waves reinforce, and where you get dark fringes, it's where the peak of one wave meets the trough of another, and effectively the waves cancel each other out. But think about how wacky that is when we're talking about electrons. We're talking about particles there that cancel each other out. We call this wave-particle duality, and again, it's one of those scenarios where it's more helpful in this scenario to think of electrons as waves, and there are other examples of that too. So wave-particle duality is a really difficult thing to wrap your head around. We started with it when we talked about photons, which traditionally were only thought of as waves behaving like particles, and I guess we're ending it with particles, i.e. electrons, behaving like waves. Now there is a formula to go with this as well, the de Broglie equation, and that is that the wavelength of these is equal to Planck's constant divided by mv. And this equation it's kind of a remarkable equation in and of itself. It doesn't look like much, but it's telling you something, This is where we're going to finish, really. We can't do much more on this revision video. There's a tiny bit left at the end, but I'm going to have to leave that. The equation's telling you something about the fundamental nature of reality. I know this is just, for A-level revision, but, I just can't help myself. Listen to what the equation's saying, because it has wavelength in it. And it has momentum in it. Wavelength is a wave-like property, obviously. It's linked with waves. Momentum contains mass, and that is a property of objects. So within this equation itself, you have this concept of wave-particle duality. Back to the start, then back to our checklist. Okay, we're way over time, and I guess we're going to leave the calculation of radiation pressure on a surface absorbing or reflecting photons for another time, because I realise we're probably over an hour now. So it's only a small one. Look up in your revision guide. It's right at the end. Again, my name is Mr. Ridd. This has been a Carl Cymru e-sgol session, supporting you, I hope, with your understanding of the topic of photons 2.7 AS Unit 2 Physics. Thank you, and bye-bye.